Okay. All right, so hopefully you had some time to use Pythagorean theorem for this. Again, this is just another sort of recap of trigonometry that I would like us to really understand, because then it's going to lead us right into special right triangles. I'm just going to get a couple colors to make it pop, and we're going to have some fun. So we'll spend a couple days on, this is a different book, so this is 9-1, 9-2, 9-3, so I just numbered the pages 1, 2, 3, 4, 5, 6. So it's 3 pages, 6 sides. I'll connect in the room here. Connect. Okay. Boop. All right. Matthew, I know I've asked you to do a lot. You want to just lower that screen for me? Thanks. All right. So Pythagorean theorem, if you recall. So first, I just want to make sure that, let me see this, get this into focus a little bit better. All right, get my own calculator. So I just really want you to understand that trigonometry is a ratio of the side lengths. All right, a ratio of the side lengths. Okay. So you've got your calculator handy. So we're just going to start, you know, in the past we learned about triangles and the relationships between their angles and sides. Today we'll take a deeper look. And I know we've kind of already had it. Again, this is just hopefully a nice, really good wrap-up for a great score on your test. So to start, each of the angles in question number 1, mark the shortest side red. And if you printed it in color or you're using Cami, it's already red. And then the medium side is blue, and the longest side is green. So you know that to be the hypotenuse is going to be green. Let me find a red. Okay, so if you just want to outline that, I know I have a lot of math tools, but even if you just want to use the edge of your binder or something, just to kind of make those straight, or if you do have a ruler. So red is going to be the shortest side. And then I'll make the middle side blue. And I'm going to kind of keep this color scheme up into the next week with, it's called special right triangles. And then the longest side is going to be green. So we know that in a right triangle, the hypotenuse is always the longest side. I hope we know that. Hypotenuse, always the longest side. Why? Because it's across from the biggest angle. Sorry, obviously it's been quite a weekend with me not writing. That's kind of messy. All right, so let me do the longest side, green. All right, so find all that. Did anyone find this hypotenuse for me? Matt?
The one all the way to the left, right?
Yes.
6.46.
Awesome. All right. And how about this short side? Anyone get that far? Did you get that far? Go ahead. 2. Good. And what's missing over here? This is a 5 in case you can't see it. And I'll highlight these other ones. And how about this one? Did you get that far? No? Okay. Matt's on fire today. 7.19 is, yeah.
Just for future references, there's this
So what, you mean this one?
Yeah.
What does it say?
6.45075341444. Like for the rounding decimals.
So when you did, well, it's round to the nearest hundredth. So are you on the second one?
No, the first one we just did.
The first one? So 3.7 squared plus 5.3 squared is, take the square root of that, and no, it's 6.46.
When we do it, like SOHCAHTOA, it gives us a different.
Yeah, so that's why I said just do Pythagorean for now.
Okay.
We're going to pretend we don't know our SOHCAHTOA yet and just prove both ways with that. Okay, so what do all these triangles have in common? What do they have that's different? Okay, so a couple of things that I hope that you're starting to recognize is that all of the triangles have the same angles. So this was a right angle, this is 35, this is 55, 35, so then that has to be 55, that's a right angle. That's a right angle. If that's 55, then this has to be 35. So all angles are congruent. Okay. They're all right triangles. But they have different side lengths. Okay, so if you didn't use colored pencils, go ahead and look at my sheet and just fill out this chart. So in triangle ABC, so that's this one all the way on the left. Let's kind of darken these in case you can't see those. A, B, C. Do the red over the green. I mean, we could call it short over longest or that. So go ahead and do this. Every ratio of red over green. Red over green, red over green. Then do blue over green. This is triangle DEF in the middle. And this is triangle GIHI on the right. So go ahead and take a minute or two. Alright, so at home by now, I hope you know to pin just the presentation so you can see it a little bit bigger if you need to. Okay, so just to kind of move things along, red over green in this first triangle is 3.7 over 6.46. And when I divide that out, 3.7 divided by 6.46, I get about 5.57. DEF, red over green, is 2 over 3.49. Make this a little bit. 2 over 3.49 is 0.57. And in this third triangle, 5 divided by 8.76 is 0.57. So you probably see where this is going, that the red over the green Red over green is opposite this 35-degree angle. Opposite over hypotenuse. So you just chose the sine of 35. So the sine of 35 degrees is always, okay, let me scoot over. Nope. It's hard to go backwards in a hover cam because it's like backwards from what you see. Did you ever present back in the day in junior high or anything and you go up to the front and you're like, wait, it's backwards. Okay, so if I were to, and again, this is kind of a review, so you already kind of know the answer, but if I took the sine of 35, what are we going to get? Millie, what am I going to get? What was the sine of 35 3 times over? 0.57. So it's kind of cool. Kind of cool, right? Okay, so blue over green for the first triangle is 5.3 over 6.46. 5.3 divided by 6.46 is 0.82. Blue over green in this second triangle, 2.86 over 3.49. 2.86, oopsies, 3.49 is 0.82. Now that one had to be rounded a little bit. And then we have 7.19 and 8.76. 7.19 and divided by 8.76 is 0.82. So blue to green from this 35, blue to green from this 35, this is going to be the cosine. So the cosine of a 30-degree angle is adjacent over hypotenuse, but on your calculator, cosine of 35 is going to be 0.82. So no matter what the side lengths are, the ratio is what's key. So you're talking about the ratio is always, always, always the same. Okay, red over blue, 3.7 over 5.3, 2 over 2.86, and red over blue, 5 divided by 7.19. All right, so red over blue, so this we know to be the tangent, which is opposite over adjacent. So if I were to hit the tangent of 35, it would give me 0.70. So if I were to hit 3.7 divided by 5.3, what am I going to get? .70. Because that's what that ratio does. It's the comparison. 2 divided by 2.86 is 0.70. I mean, it takes some rounding, but 5 divided by 7.19 is 0.70. The 5 bumps up, so it's like 69.50, so it bumps up to 0.70. So what we chose here was the 35-degree angle. We could have chosen any one of these, and you could have verified that the ratios are always the same. So, Haneen, what do you notice about the ratios? How are we answering this? They're the same. Even if they were whole numbers, they're all the same. So even though these triangles are different lengths, the ratios are the same. So this is saying, what do you notice about the ratios? So the ratios are the same for each triangle. Okay, so now let's go backwards. so that you can kind of understand this ratio concept. I'm going to tape this because I'm really hanging on to dear life there. Okay, so use the diagram to find all missing sides and angles if the tangent of 18 is 1/3. So remember, it's a ratio. So if the tangent of 18 is equal to opposite over adjacent, which is 1/3, and I have 2 over something, what's that something? 6. Alrighty, so if this is our x value, that's 6. Okay, so for some right triangle, let me draw a triangle. The sine of A is 0.6. So let me pretend that this is sine A, and 0.6 is literally, you say it, is 6/10. So from A, I'm going to say this is opposite over, sine is opposite over hypotenuse. So 6/10. Okay, what could the side lengths be? Okay, they could be. What could they be? So you know this is a triple. Any 3, 4, 5 doubles is a 6, 8, 10. But even if you didn't realize that, you could say, oh, okay, because these could be the sides of it. These could be the sides of it. So if you did a squared plus b squared equals c squared, 6's always look funny. B squared equals 10 squared. So you could do Pythagorean theorem, you could recognize it as a triple, and now eventually we can use our trigonometry because every single angle has the same ratio of its sides. There's only so many ways that you could open up that paper clip. Okay? So no matter what size paper clip you have or fastener, however much you widen it or narrow it, it's going to be the same ratio of sides. All right, opposite over hypotenuse, adjacent, and so let's kind of formalize that. So on the back here is quick notes to make. Okay, so, and again, I know we're going backwards, but this is what I'm hoping that this really reinforces it, because you're going to use it for special right triangles, and we're going to use it for something called the unit circle. Okay, so finding angles and sides. In a triangle. I should white this out and say in a right triangle. Okay. We know that the sum of the angles, this is really important, which is the first lesson we learned almost this year. Sum of the angles in a triangle is 180 degrees. And that a squared plus b squared equals c squared for a right triangle. And c is always the hypotenuse. Hypotenuse. Okay. So the acute angles in the triangle now remember, acute is less than 180 or less than 90. So it's the other two angles. They're complementary. So that's why on the other side, if one was 55, the other one had to be 35. Okay? The acute angles in a right triangle determine the ratio of the side lengths. So we already know sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. If you want to see the picture, and if we're going from this angle, usually it's called theta. I know sometimes I used alpha last week. But you've got your hypotenuse is always, always, always across from the right angle. So it's always the longest. Oh, I should have used the same colors I used on the other side. This was always green. And then, what was the short side? Red? Well, it doesn't matter. Okay, opposite. I have to abbreviate that because I'm going to be off the grid. And adjacent. If you're going from this angle. Okay, so let's kind of reaffirm that we're drawing a right triangle with cosine of 60 is 0.5. So you're going to draw a right triangle to start. And one of the angles has to be 60, right? So if one of them is 60, then the other one is 30. Okay? So if the cosine of 60 is 1/2, and that's adjacent over hypotenuse, let's go from the 60 and call it 1/2, because that's adjacent over hypotenuse. And maybe you liked it when it was 0.5, so if you did 5/10, that's okay too. That's the beauty of this. Okay? So, what do we want to use? 1 and 2 or 5 and 10? Maybe I'll stick with 5/10. That seemed to resonate with people. I'll kind of wipe this out. And it doesn't matter because the ratio is what matters. The ratio is what matters. Okay, so if I say the cosine is 1/2, that's adjacent over hypotenuse. The adjacent is from 60. The adjacent is 5 and the hypotenuse is 10, so I've got 5 squared plus b squared equals 10 squared. Hopefully I can just go right into 100 minus 25, which is 75. First semester, you did the square root of 75, which was 25 and 3, 5 root 3. Remember that? Those were the days, huh, boys and girls? Bet you thought you'd never wish we'd miss radicals. But now we can get an exact and rounding to the near. This is technically exact. Rounding this to the nearest, oopsies, square root of 75 is 8.66. So if I were to divide 8.66 over 10, that would give me the sine. And if I said the sine of a 60, it should be the exact same, which it is. Okay. So there is more than one possible answer for something like this. I just did one thing. So I would like you to finish up numbers 2, 3, and 4 for homework. Okay? If you want to move on and kind of start some of the 9-2 stuff, okay, we are going to watch this fun little video, and I hope you have a great day. All right, you're welcome, hon. Bye, guys. Bye at home. You too. Thank you.